Okay, so let's see one last application, which is using Bootstrap to estimate the bias of an estimator. And then we're done for the week. Recall that the bias of an estimator theta hat for a parameter theta is given by the difference between the expectation of theta hat and the true value of theta. The Bootstrap estimate of bias for an estimator theta hat is given by bias hat, which is equal to the mean of theta hat b minus theta hat across the total of large B Bootstrap replications. Here, theta hat b is the beef independent Bootstrap replicate of the estimator. That's essentially our TB, which is the statistic or the estimator calculated with the beef Bootstrap sample. Theta hat is the estimator computed with the original sample of size n. So the statistic calculated at x1 all the way up to xn. You can see that in Bootstrap estimate of bias, the theta hat replaces the true value of theta in the original bias formula. We're going to see two examples where we develop estimators, in fact, maximum likelihood estimators for some unknown parameter. We use Bootstrap to calculate, to approximate its bias, and then we'll compare it with the theoretical value of the bias. The first example involves the estimator for the uniform upper bound, and the second one involves the estimator for the population variance for normally distributed random variables. Okay, so let's see our first example where we are having an estimator for the uniform upper bound. Suppose x follows the uniform distribution between 0 and theta. Theta is the parameter of our interest, and theta is the upper bound for the uniform interval. Given a random sample, x1, x2 to xn from this distribution, the maximum likelihood estimator for theta is theta hat, which is equal to xn, the nth order statistic. Simply put, this is the maximum of our n samples. So the MLE, which is the maximum of the samples, is actually biased. You might have known this from 510 or 410. So in this case, we know that the expectation of the nth order statistic, or the maximum, is actually theta times n divided by n plus 1. And thus, we know that the theoretical bias for this MLE is given by the difference between theta and the expectation, and that's equal to negative theta divided by n plus 1. So that's the theoretical value. Here, what we're going to do is we're going to use Bootstrap to estimate the bias for the MLE. And let's see whether that agrees or how it compares with the theoretical value for the bias. Without loss of generality, let's choose theta equals 1, and we'll use the sample size of 100. Our first step is still to draw the samples from this distribution. So we're going to draw a total of 100 samples from the uniform distribution between 0 and theta. Here theta is 1, so that's just the standard uniform distribution. We're going to do a total of 10,000 Bootstrap replications. But before that, let's calculate theta hat. So that's the MLE evaluated at the original sample x, and that's the maximum of x. Let's now create a vector theta b's, which are used to store the theta hat b's. In other words, the estimator evaluated at each of the Bootstrap samples. For each b between 1 and large B, we will first do the resampling from x. We draw a sample with replacement from x of size n, and then we calculate theta hat with this Bootstrap sample, so the maximum of xb. The bias estimate, if we apply the Bootstrap bias estimate formula, is given by the mean of the difference between theta b's and theta hat. And in this case, that gives us negative 0.008. So this is slightly different from the true bias of -1 divided by 101, which is approximately equal to -0.01, but you can see that it's actually quite close. For our second example, we are going to look at the estimator for population variance. Here, if our data, so if x follows the normal distribution with mean mu and variance sigma squared, then the maximum likelihood estimator for population variance sigma squared is given by sigma hat squared, which is equal to 1 over n times the sum from I from 1 to n, xi minus x bar squared. So x bar is the sample mean. You know that this thing is biased. So the bias of this MLE, sigma hat square, is equal to n minus 1 divided by n sigma squared minus the true value sigma squared, and that's equal to -1 over n times sigma squared. So let's see if the bootstrap estimate for the bias of the estimator for the MLE will be close to this. And without loss of generality, we will test this on x follows the normal distribution between with mean 0 and standard deviation or variance of 1. And sample size is equal to 25. In this case, we can plug in n and sigma squared into this bias formula, and we know that theoretically the bias should be equal to -1 divided by 25, which is -0.04. Now let's write the code to obtain the bootstrap estimate of the bias. N is equal to 25, and we're going to do 10,000 bootstrap replications. We first generate our x values, which are 25 values from the standard normal distribution. The MLE evaluated at the original sample is the mean of the square deviation between the x values with the sample mean. And then let's find the equivalent across the bootstrap replicates. Here across the bootstrap replications from, for B in 1 to large B, we first do the resampling. So we sample n values from x with replacement, and then we calculate the corresponding MLE using this bootstrap sample. In the end, we apply the bias formula and then calculate what is the mean of the bootstrap variance estimates minus the variance estimate using the original sample. And that gives us -0.047, which is quite close to the theoretical value of 0.04.